Yep. So I showed off something I was working on at the last Telecon, but there were not a whole lot of people in attendance that time. I It started making a spreadsheet basically of PyHC dependency conflicts. And I had made a spreadsheet with the core PyHC packages at the last meeting. And then I since wrote a Python script to basically automate generating the rest of the environment. And I have a really interesting and informative looking couple set of tables here that I'll share my screen and show off. But the weird thing is that I have not been able to find an actual dependency conflict yet. So I'm confused by that a little bit. Um, Here, this is going to be zoomed out way too much for anyone to actually be able to see. So that's okay. But basically what we're looking at here is along the top rows here, I'll zoom in a little bit so you can kind of see a little bit, are the PyHC packages. Like here's the core ones, and then starting at column J all the way to the right of the rest of them. And what I've done is basically went through and used a dependency tree tool called pip dep tree that just lists all the dependencies that the package requires and then recursively lists those dependencies. And then this script goes through and then combines up and basically figures out, okay, what's like the allowed range of every dependency for every project. So like for Komodo, this very first, well, I'm not going to pronounce that Python package name, but all of the rules add up such that it needs version 4.7, and all the rules for this package here add up so that it needs this. And then I go horizontally across the table and combine all of the rules. So like NumPy is a popular package here. So let me scroll to the NumPy row. Again, probably way too small numbers to see on the screen, but pretty much every package uses NumPy. But if we use a version greater than or equal to 1.23.0 or less than 1.24, it'll work across all of them. So there's a total of how many rows here? 240 dependencies, 240 unique dependencies if you want to pull every PyHC package into one environment so far. Although I have these yellow columns here, these packages do not actually list their own requirements. So dependency tools like pip dep tree don't actually know what these packages require. So I might do some digging myself to try to figure out what they are. So where to take it from here, I'm a little bit confused because I myself have struggled to install even just like, a handful of our core packages into the same environment together. And now I'm questioning whether or not I started from scratch or if I already had like a version of NumPy that I was just like not refusing to update or something. I don't know. But anyway, theoretically, I now have a list of packages and allowed version ranges that if we set up an environment with, we would at least be able to have all of the latest versions of a majority of the PyHC packages in the same environment. So what this teaches us, I'm not entirely sure, but it's a way to get a handle on the problem. And there are enough tests in my Python suite here to know that this does actually work. If there were a true dependency conflict, we'd get like a red cell instead of a green cell, and it'd tell you what rule was disagreeing with the allowed ranges over here. So maybe it'll be useful in the future to have this kind of thing.
The fact that there's exactly one minor version of NumPy that works is kind of scary.
It's definitely restrictive, um, but possible. So I don't know. I mean, if anything, this can give us a sense of where projects are at. I don't know. Maybe the Helio Cloud group might be the best people for me to discuss this with because you guys are actually in the business of spinning up environments with all of these packages. So maybe you've found more issues than just version conflicts that I'm not aware of. But yeah, um, that's pretty much all I had up. I see a question for the Komodo package. Did I use kamodo-core or Komodo CCMC? Komodo-core. I would have used Komodo-core for that. I could throw in the CCMC version, but I don't think that version's pip installable yet, and my Python script is pip installing all these packages. So anyway,
So would it help? So this is Rebecca speaking. Would it help
yep.
if I sent you a conda list output from an environment that Komodo is installed in, like the CCMC one?
It wouldn't hurt. Yeah, if you wanted to email that over to me, I could just take a look
Okay.
at it and maybe manually include it in the table if anything.
Okay. Because I
Yep.
know that pip install is waiting on that pip install capability for the CCMC one is waiting on spacepy to accept our pull request because we depend on a certain feature for the for one of the interpolators. But I had a second question, if you don't mind.
Yeah.
What are the packages that limit the higher versions of NumPy?
That limit the higher versions of NumPy. I mean, I
I
would
think
have to,
SciPy might be doing that now, actually.
Really?
Yeah,
yeah, I
there are a
would have
couple
to
of
go through.
packages that do the that set the maximum version to the largest version that is currently released,
Hmm.
based on the theory that you can't guarantee that the new version won't break it.
Okay.
Yep. I do know that by and large, less than 1.27 is what the majority of packages require. I think there was like one non-core package, like maybe like a Michael Hirsch project or something that had less than 1.24, which is what dropped it down to this. But if we excluded like one package, this would be less than 27, not 24, if that makes it any better. But yeah, that kind of stuff is happening. And that's part of the reason why actually there's so few conflicts is by and large, there are very few requirements that say less than a version. By and large, requirements are just greater than or equal to something. So in theory, you could always upgrade to a later version. And then at least according to what these packages are self-reporting, we're not breaking any requirements. I say self-reporting as long as they're actually listing truly what requirements their package needs, and this tool is recursively finding all the recursive dependencies right, but it should be. Anyway, I'm longer in this segment than I expected to go, so I think I'll go ahead and stop sharing my screen and turn the conversation back over, but that is where I'm at with that effort.
Hey, Rebecca, you said you're waiting on a pull request from us. Is there an open PR or is it something that we've merged but we haven't cut a release yet?
Ooh, good question. So I left this in Lutz's hands.
Okay, we
I
can follow
don't
up offline.
remember. Yeah, okay, sounds good. Thanks.
Awesome. Well, thanks for updating us, Sean. All right. So today we have Kristopher Klein on. He will be giving us a bit of a HelioSwarm mission overview, and talk about how hopefully we might be able to help out as PyHC leader. Whenever you'd like to take the floor.
Sounds good. So first of all, let me make sure I'm sharing the right screen. Thank you very much for the opportunity to speak today. You all seem to be a very a crowd willing to interject, and so please feel free if you have questions at any time. Let me know, and I will do my best to answer them and address them. So this presentation is meant to give an overview of a mid-X mission, HelioSwarm, whose goal is to study the nature of turbulence in space plasmas. It was recently selected no longer this year, last year, as one of two heliophysics medium class explorers, the other being Muse. And the novel thing about HelioSwarm is we're not going to be sending 1 or 4, but rather 9 spacecraft into this near Earth environment. And in doing so, try to disentangle spatial and temporal scales of turbulence in space plasmas. And so what I'm really hoping to get to today is just provide a brief overview of what is turbulence to make sure we're all on the same page about it, and then provide some details on what this HelioSwarm observatory is going to be. But most importantly is to start laying the groundwork for how can HelioSwarm and the broader solar wind community use tools like PyHC to really take full advantage of the data that we're going to be drawing down from this mission. One of the things that we've been talking about internally is the worry that we're just going to have people plotting nine time streams of density measured at 9 different spacecraft and say, I can see by eye that there's this little bump right here at 12 o'clock, and therefore it makes sense. And that's not really going to help us grab the richness of the data. And so one of the things that I'm really hoping to do is making sure that we have the tools in place to work with this rich set of data prior to the data coming down, rather than waiting until the mission is already flying. Rebecca, you noted that you already have tools in PyHC to help with mission planning. I am not aware of those, and so if you could either pass along the names of those either in the chat or to me, that would be useful. A lot of the mission planning, and we'll get to the specific details of where the spacecraft are going to be and their configurations later on in this talk, has been developed by an excellent group of flight dynamicists at NASA Ames that have a lot of their own homegrown tools for actually making sure this murmuration of spacecraft are in the places that we want them to be at different points in the mission. But if there are tools that are already available, I would certainly love to hear about them. Perfect. This is being recorded, right? So I don't have to attempt to jot down every single one of these items.
No, I will be sure that everyone gets these.
Perfect. Thank you. And also just to note, this is what I'm presenting today is the work of a broad group of people. We have 2 other members of the team, or at least last time I looked at it, 2 other members of the team on the call, both John Niehoff and Ben Maruka, both hiding behind no cameras at the moment, but they've been instrumental in various elements of this as well. So first of all, making sure we're on the same page. If you put a dozen turbulence theorists in a room and require them to write down in a single sentence what is turbulence, you'll get 13 different answers. But if we have a single sentence, the best we could come up with is turbulence is multi-scale disorder. It's this idea that you're trying to understand the flow of energy from where it's injected, typically at very large scales, how it mixes up, how it transfers energy, mass, and momentum from scale to scale to scale through what we refer to as a cascade, and then how it's eventually removed from that system. The poetic way of describing that is in the upper right-hand panel. Lewis Fry Richardson's big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity, is basically a statistical description of this transfer of energy. And so a lot of the effort over the last 100 years in understanding turbulence has really focused on trying to come up with different statistical models for understanding each of those different colored arrows, how energy is injected in, how energy is processed through, and then removed from this system. And this is true for the cases of fluids, for gases, or plasmas. However, plasmas pose an interesting problem because they are more complicated in a lot of really interesting ways. They don't have just this neutral fluid behavior, but rather they have the electric and magnetic fields. And because of that, you have new physics that's being injected into the system. And you have the magnetic fields that are going to, in some sense, orient that transfer of energy, restricting the transport in some directions and enhancing it in other directions. You're going to get the formation of different kinds of current sheets. You're going to get different kinds of intermittency that might arise and affect the kinds of dissipation that will actually happen. And in the solar wind, for instance, the collisionality is sufficiently low that viscosity, that final line of the Richardson poem, is not going to be the first physical process to be invoked, but rather you have all of these other possible processes for removing energy from the system. So so we have this more complicated setup that we'd like to really explore, and we also think that it's pretty important to understand, not just from an abstract sense of things, but in order to understand this whole universe of different environments. Basically, I mean, we're on the PyHC call, so I probably don't need to make this pitch to you, but understanding plasmas across the universe is important for understanding stars that we receive photons from, the interstellar media, the accretion disks, and importantly, a lot of our understanding of those distant phenomena are informed by using our local measurements of the solar wind as a natural laboratory for understanding all of these universal processes. Now, I know that any laboratory physicists that might be on the call may cringe at the idea that, right, we're not ordering up one particular beta at this particular time, but because we have a large volume of data to work with, we can look for a time where beta is 10 and density is low and temperature is high, or whatever conditions we're looking for, and then study that as a particular case study. So what is it that we want to understand about turbulence? Well, in the concept study report for the mission, we broke it down a little more granularly than this, but generally we want to understand what mechanisms actually lead to the energy cascade between the different scales, and how is that impacted in different kinds of turbulence, whether it's turbulence that's been slowly decaying since it was launched off the sun 3 days ago, or stuff that's been much more recently driven by CMEs, CRRs, or even processed through the magnetosphere or the magnetosheath. We want to understand how the energy is actually distributed in space and time, and how the intermittency, those really intense current sheets, interact with the larger scale turbulence, and how they lead to different kinds of heating of the protons. We have a few different white papers that were published much earlier on, and we're also working on finalizing an overview of the current state of the emission paper that hopefully will be distributed in the not too distant future, and sent out for publication as well. So those are the open questions we're trying to understand. Why can't we just do this with the tools that we have at hand? Well, if you have just that single spacecraft, you're effectively just flying along that single solitary line through this very complex structure, and you can construct spectra. You can construct some limited statistics from that single measurement point, but you are fundamentally limited in making some assumptions about your ability to convert between time and space that assume that that put certain limiting restrictions on the dynamics that you're able to actually access. Right. What I've written here is effectively Taylor's hypothesis, the idea that if you measure a certain time series, you can equate that to a particular spatial scale. You can make these nice spectral power laws and make arguments comparing the slope in these different ranges, where you have very low frequencies where the energy is being injected in. You have the inertial range with the Kolmogorov-like index, and then you have some scale where energy is being removed more quickly than it's being transported to smaller scales, and what we refer to as the dissipation range. The difficulty is that a lot of the different theories that we have give us very, very similar spectral indices, and therefore it's very difficult to definitively say, clearly this is the right model for turbulence in this case, because it's pretty hard to tell the difference between a 5/3 and a 3/2 spectrum with a strong degree of certainty. So what have we done? Well, we've flown missions with multiple spacecraft before. Missions like Cluster, a mission like MMS have sent up 4 spacecraft that have been organized in these nice tetrahedral configurations, which allow us to access not only just this single worldview through this dynamic system, but rather actually look at the spatial structure at a single particular scale at a particular point in time. So both MMS and Cluster have been optimized to focus on these single scale measurements, getting the full structure at those scales and changing what scales they access throughout the entirety of their particular mission. But what we're going to be doing with HelioSwarm is not restricting ourselves to a single scale at a particular time, but actually looking at that multi-scale disorder, having the ability to assess structures that are both on those very large, those MHD scales, at the same time as pushing our way down into those ion kinetic scales. That's the design restrictions that we're working with, trying to cover multiple scales simultaneously with all 9 of our spacecraft. Now, this tells us exactly how far we should make sure the spacecraft are separated. If we use our previous measurements of the solar wind to get an understanding of what physical scales we should be looking at, we can look at things like the ion gyroscale. This right here is a probability distribution function drawn from decades worth of measurements from the WIND spacecraft. We see it's typically around 100 kilometers. It has some variation. The larger scale transition, what we're referring to here as the break scale, is usually around 1,000 or 1,200 kilometers. And so we want to make sure that these separations between the spacecraft will encompass both of those scales simultaneously and also be much larger and much smaller so that we can simultaneously look in that magnetofluid as well as the sub-ion scales at the same time. This also drives how quickly we want to make sure that the instruments that we will be measuring with are functioning and making sure that we're capturing the full range of the solar wind that we're going to be seeing. And so that leads us to the actual environments that we're going to be working in. Hopefully the video is playing. I'll wait for a thumbs up or whatnot to make sure that's coming through.
Looks good here, Chris.
Thanks. So we're not going to be sitting out at L1. Rather, we're going to be in this nice lunar resonant orbit, going out to about 60 Earth radii and then going back in to about 12 or 15 or so. Because these orbits are much further out than a lot of your purely magnetospheric missions, we're going to be sampling different kinds of solar wind at different points in time. Either this pristine solar wind, basically what I've highlighted here in red, which is going to be that stuff that's mostly decayed away as it's been launched off from the sun several days past. We're going to be going through the magnetosheath, the magnetopause, and into the magnetosphere for some fraction of the mission, what I've highlighted here in blue. And then in green, that's going to be the area that's still magnetically connected to, and thus will have turbulence that's going to be driven by different kinds of foreshock waves by its connection to the magnetosphere. So we're going to have these different times where we have different kinds of plasma, but importantly, and just for reference, I didn't say this out loud, but the hollow circle is the moon, giving you a sense of the distances we're going to be covering. All 9 of the spacecraft are going to be in basically that little, what's that, a pentagon? Yeah, that's a pentagon, in that kind of small distance there. So the actual configurations that we're going to be working with are going to look something more like this. So I've taken, hopefully that spirograph image from the previous slide is familiar, and now zoomed in the central spacecraft, which we refer to as the hub, is this central point right here. And then there's going to be 8 nodes that are surrounding it, and the flight dynamicists have worked out trajectories that will leave some of those nodes very, very close to that central hub, separations on orders of tens of kilometers, while others are much more far flung out to thousands of kilometers at any given time. These three different panels are showing two-dimensional projections of those relative separations. And again, we'll have these be able to sample that multi-scale nature of the plasma in all of these different environments. So for the aficionados in this group, and I see at least some of you probably are, this is going to be somewhat different from MMS or cluster. And just to highlight that difference, I'll draw your attention to this bottom plot right here. These open circles that are orbiting relatively quickly around are two different intervals from the cluster mission, which their apogee and perigees were much closer to Earth than helioswarms are going to be, which means that they never really got out into the pristine solar wind for significant periods of time. And also the tetrahedral formations, the actual ideal configurations were kept to much shorter periods of time just because of flight dynamics restrictions. That's maybe seen more easily in this right-hand plot, where we showed basically the shapedness of the overall tetrahedral formation on the x-axis, the actual size of the tetrahedra on the y-axis. The blue and red are two different time windows for the cluster mission, and you see that those tetrahedra change rather dramatically. The black dots are the 126 different tetrahedra formed by the 9 spacecraft in the HelioSwarm observatory, and we see that they change over a much more at a much more sedate rate. I see something popping up in the chat. Slightly. Rebecca is asking, will the sample the solar wind both above and below the ecliptic plane? If we go back to one more back, it looks like, to this plot. So here we see apparently my mouse is deciding to freeze up, but hopefully you can still see in that lower right-hand panel. The spirograph view here is the XZ GSE environment, and you see that we will sample out into the solar wind. So all of those red intervals at regions between about +5 RE GSE, maybe 3, all the way down to about a minus, let's call it 12 or 13. And so there is some variation there. It's not significantly out of the ecliptic, so we're not going at huge deviations, but it is also not sitting at L1, so it is a different environment than, if you're used to working with wind, ACE, or stereo. Jonathan?
And yeah, I think most of our apogees are going to be in that below the ecliptic plane region, right?
Yep. Yeah. Most of the apogees are sitting in that kind of 10 to 15 sort of environment. And that's, we're using a lunar resonant interaction basically to get the right swing bys that we need to get us into this orbit with the amount of delta V provided. And so that's where that's the environment that puts us into. Does that, oh, go ahead.
No, it's just, one of the things that took me a while to get my head around while we were doing this is that our prime science really is out at those apogees, because that's, it's getting us up onto the solar wind. It's also where we're slower in the elliptical orbit. So we kind of have some hang time there. The satellites aren't moving a lot relative to each other. So it helps to think of kind of a series of successive campaigns out at apogee. That's where the real meat is.
The one thing that I do want to highlight for those, again, who are focused, who have experience with cluster or MMS, is that a lot of those previous missions were really focused on having some sort of scientist in the loop or CITL kind of setup. Our philosophy for the measurements we're taking is we're going to draw down all of the measurements that are being made and not do any pre-selection. So if you are interested in times where it's not at apogee and maybe it's not in the ideal geometric configuration in terms of having a two perfect tetrahedra, we will still be bringing that data down for analysis by the community. Does that answer your question, Rebecca?
Yes, a lot more detail than I could have admittedly follow. So thanks.
Certainly. So this just highlights some of the words I've already said in terms of we're going to have this central hub, we're going to have those nodes. Unlike MMS or cluster, where each of the individual spacecraft are actually directly commanded, all the commands are going to be sent through the hub and then sent out to the nodes then report back to the hub. And so the engineers on the team have done a tremendous job of preparing us for this kind of operation. And I will not speak to their subject matter expertise, but I can point to the right people if you're interested in any of that. What are we actually measuring? That's probably an important point for you all who are interested in actually getting your hands on this data. We're going to be measuring the at all 9 points, both the magnetic field and the local proton conditions, right? We're going to be measuring the magnetic field using a combination of two different kinds of magnetometers, both flux gate and a search coil magnetometer, to really cover that full range of the frequency response that we need for this mission. And then also at each measurement, measurement point, each of the 9 spacecrafts, we're going to be measuring using a Faraday cup to give us plasma density and velocity. All of these instruments are very high heritage. They're things that are currently out there in the heliosphere in various forms. And then on the hub, it's going to be, in addition to those 3 instruments, a higher higher energy resolution measurement of the for an ion velocity distribution function for an IESA, which is similar to the one that's currently flying on Solar Orbiter. So for those familiar with that instrument as well. We also will have an electron electrostatic analyzer that's going to be part of a student collaboration option, basically teaching the next generation of engineers how to build spacecraft instruments. So that's the kinds of instruments we're going to have. For those who are interested in, well, what are the actual products? What are the actual kinds of cadences we're looking at? We're going to have both the basically covering the magnetic field data from DC all the way up to 32 samples per second. So really focusing on those ion scale physics. We're going to be measuring the proton density, velocity at an 1/8 of a second cadence as well. And then the proton temperature and the proton temperature anisotropy as reported by that ion electrostatic analyzer will only be coming from the hub. We'll be bringing the whole VDF down, not just reporting onboard moments. And we'll also be able to measure both the protons and the alphas and really resolve those quite well with the ion ESA. And again, we are working on writing these details up for an overview, a mission overview paper, which hopefully will be submitted this semester. So as Jonathan already alluded to, at different points in the mission, we're going to have different configurations. That's how the flight dynamics will work. The 2 ways that we're quantifying those configurations is by looking at the actual baseline structure, the actual baseline separations, and making sure that we cover the 3-dimensional structures for all of the different baselines. If we have 9 spacecraft, that gives us 9 times 8/2 different possible baselines. So that's 36 for those like me who need to have an actual table reminding them of the combinatorics. And so we identify particular intervals where we have the vector component of those 36 baselines spanning the full three-dimensional space as good three-dimensional hours. And we count the number of those good three-dimensional hours. Those are the times where we've highlighted it in a solid line out here, as opposed to just the general dashed line where the observatory is actually going through. So those are the times where we cover all three of the regimes in all three different orthogonal directions, giving us the ability to fully resolve the three-dimensional structure of the turbulence there. The other kind of configuration that we care about, which I've already alluded to, is looking at the different tetrahedra that we can form. And so this is maybe a clearer way of actually demonstrating those tetrahedral configurations. And so for a quantitative sense, we can basically calculate the eigenfunctions of the volumetric tensor defined by the position of those spacecraft, and then look how planar those eigenvectors are, how elongated they are, and define a tetrahedra as being either pseudospherical, that is relatively regular, or in one of these more flattened or elongated shapes, pancake, potato, or sausage, for instance, being ways of quantifying that. If you're looking to calculate things like spatial derivatives, you really want to have less elongated structures. And so what we've done is, if we said, well, let's look for hours, which, if this loads, have very regular tetrahedra that arise at multiple scales simultaneously. So what you can see is, while we're near apogee, as we're at our farthest place away from the Earth, we will have this singular central tetrahedra that is very regular and has a scale separation of about 100 kilometers or so, and then also at a second, third, or sometimes even fourth tetrahedra that has a typical size of 100 or 1,000 kilometers, 500 or 1,000 kilometers, thus giving us the ability to sensitively look at the structure of the spatial structure and the spatial derivatives at multiple scales simultaneously. So that's the nature of the mission itself. One of the things that we in the team have been talking about is how to actually help the community actually work through and process all of this data, right? I've sat down and I've taken the design reference mission as it is, and I've calculated those eigenfunctions, those eigenvectors, and determined when we have particularly good hours. But rather than forcing everyone in the community to, rewrite those same scripts to reinvent the wheel, it would be good if we can start developing as a community good ways of actually working through and processing all of this rich data set, but probably also somewhat complex data set. You're right, we have to work on making sure that we have good ways of integrating in 9 different time streams from 9 spacecraft, but 28 different instruments, and then applying the different analysis techniques that we'd like to it. So that's one of the things that we're currently working on, and Jonathan is currently working is leading the effort of pulling together a design reference mission that would be publicly available for the community to actually, say, run these different and their favorite turbulence analysis through their favorite numerical simulation, for instance, with the different configurations that we're actually going to have. And so I can talk also about some of the ongoing analysis techniques that we've started to pull together, and that I would like to implement in an open source fashion. But I'm going to take a pause here for both a drink of water and see if there are any questions before I dived into that element. Hearing complete silence, I will bash on to one of the example kinds of analysis techniques that a grad student of mine, Teddy Baronin, has been working on implementing for the HelioSwarm mission. So for those of you that are familiar with cluster and MMS, everything you see on the screen in front of you hopefully is somewhat familiar, but one of the typical tools that was developed actually back in the late 80s was the first time this particular tool arose in the geospatial context in a PhD thesis, was a tool called the wave telescope, or K filtering, that basically said if you have measurements of, say, the magnetic field at 4 different points in space, you can't do a spatial Fourier transform in order to look at what watch a wave actually cross over that structure. You're just measuring it in too sparse of a fashion. And so can we work out a different mathematical tool that lets us calculate the power spectral density as a function of a spatial location? And so it was developed then over the next decade in preparation for the cluster launch, and has been used both for cluster and MMS. Basically, you need at least 4 spacecraft in order to do this inversion and this evaluation of the power as a function of both frequency and K. This plot right here, which is what's labeled A, and I'm sorry, but my mouse on this laptop has died, so I can't point to it at the moment, but labeled with Roberts 2014. Basically, this is a test case where he's run 8 different waves through, and is able to identify he knows the 8 waves that he threw into this particular case, is able to resolve, yes, these are the peaks associated with those waves. And so if you are trying to discern, say, a dispersion relation of a wave moving through your turbulent system, this is the ideal tool to work with. However, it only will work at particular scales. If you have a tetrahedra that's much smaller or much larger than the wave, you're not going to be able to accurately resolve that wave moving through the system. And there's been some work in the early 2000s and 2010s to identify what is the actual level of uncertainty as a function of the difference between the tetrahedral size and the wave size. However, a lot of that focused on just 4 spacecraft. And so what my grad student Teddy Baronin has done is gone through and actually learned using Bayesian inferencing what the error and likelihood of aliasing are for an arbitrary tetrahedra, or generally n-hedra, so a polyhedra with at least 4 vertices, in using the wave telescope method. Now, that he's an applied math guy, and so part of this was just doing that as an applied mathematician's as an applied mathematician, but also because he was able to learn this error, the actual error, it allows us to immediately say, if we want to look at a wave of this particular size, we know for a particular hour from HelioSwarm which of the possible subsets of the spacecraft should we use to actually analyze that particular wave. So if I can get this to play, here we go. What he's done, he's gone for the first 14-day orbit. So each of those lunar resonant orbits are basically 14 days long. He's already gone through and calculated at this particular point in time for a wave of this scale, the most accurate representation from the wave telescope method should use these 4, 5, 6, 7, 8, or 9 spacecraft, and that way you can then quickly build up and quickly automatically decide which of the 9 time streams you want to draw down in order to actually perform the wave telescope analysis. So my hope is that tools like this, where you're able to automatically provide the user, these are the time streams, these are the spacecraft that you want to actually be working with, would be something that we would like to incorporate into some actual software package. And so I just wanted to use that as one example. We also have some other examples of things like magnetic field reconstruction, using things that are similar to the Kurlometer method, basically extracting information from Maxwell's equations and doing Taylor expansions using all 128 of those tetrahedra that we can form, and then combining those first order Taylor expansions in order to reconstruct magnetic fields over relatively broad regions of volumes of space. But I think those were the two examples I wanted to touch on. And so I want to thank you all for your time, and was wondering if you had any questions, thoughts, other packages I should immediately be aware of, and wanted to just use this as an opportunity to start a conversation. I didn't mention, I just realized in looking over these, the mission is going to be launching by the end of this decade, so probably 28 or 29. So we do have somewhat of a ramp between now and then, but we don't want to be caught flat-footed and have this data, downloaded, calibrated, and ready to work with, and then say, let's start building the software pipeline now. We'd rather it be in place and rather have the whole community ready and hopefully excited to use this data as soon as we bring it down.
Yeah, thank you, Chris. I think there's a lot of potential here for collaboration, and in particular with Plasma Pi. It sounds like there's going to be a lot of fundamental turbulence functionality needs, and that's an area of Plasma Pi which we still need to really develop. So it's something that we'd be happy to work with the HelioSwarn team together. And then one other thing which came up in a actually I think the same conversation that led to this is that one possible way to make collaborations with the laboratory plasma community would be to do a simulation type experiment where you have a bunch of probes stuck in at spacings and orientations which are similar to what the spacecraft in HelioSwarn would be, and then get a mock data set, or actually real data set, and then do the same sorts of analyses. So you'd be like doing the analyses on real data for a different regime, and that's something that could be done, I guess at this point, a few years before the mission launches.
Yeah, and so we actually did some of those kinds of calculations as part of the concept study report for the mission. So we threw, for instance, the 9 spacecraft configuration through both hybrid and fully hybrid fluid and kinetic simulations, and then did a few different kinds of analysis methods, whether it's looking at temporal spatial decorrelations, whether it's looking at the higher order statistics. And so we do have some of those calculations done. None of that data has been pushed out publicly yet. It was all done as part of the concept study report. So I think that your suggestion of actually not only just outputting where the spacecraft are, but also associating that with, actual simulated data so that everyone's working with the same density and velocity inputs.
I shouldn't use the word simulated, to like actually do experiments in the laboratory, like at the large plasma device and things like that.
Yeah, I think that would definitely be feasible. I think there would be some really interesting things looking at doing the multi-point analysis techniques, especially for things like calculating things like decorrelation scales, you're going to be accessing a really different region of parameter space in terms of the ion kinetic scales and the MHD scales are going to be in fundamentally different places. You're probably going to be running into viscosity limits in a different way, but I think there is going to be some useful overlap there.
And Nick, if I can just piggyback on what you brought up, because I think it's relevant. One of the things we're looking at here is as techniques and codes get developed, we want to make sure that they're not tied to any one thing. So yes, we want to have codes that work with the HelioSwarm data stream, but we don't want people to be locked into you have to use the HelioSwarm official analysis software, or you have to use HelioSwarm data, right? So being able to have flexible modules that we can feed from a range of data inputs, but that run the same calculations underneath is really important. The other thing we're doing, and Chris alluded to this earlier, because we're starting with kind of the positioning of the DRM, is we're hoping to have a large amount of synthetic data over the next couple of years in the same file structure that we're going to use for the real mission. So we've been talking with SPDF, and we're probably going to actually have a HelioSwarm concept mission on SPDF with the data. So that, as Chris said, once we hit orbit, we can just swap out the sample files for the real files and run.
Awesome. Thanks.
Any other questions for Kristopher? Awesome. Well, thanks again, Kristopher, for jumping on and sharing about the mission with us. Please, anytime you need, feel free to send out an email to our PyHC email and ask questions, and we'd be more than happy to help in whatever way possible with the packages that we have available.
Certainly. Thank you all for the attention and the inputs, and look forward to continuing to chat with you all about this in the next what now, 5-6 years?
Sounds good to me. Awesome. Well, everyone, I'll see you again in 2 weeks' time, March 20th. Yeah, same time, same place, topics TBD. And have a good rest of your Monday.